In this video, I'll show you a fluid structure interaction simulation of a butterfly valve and reed sensor. AIM includes a number of predefined templates. Today I'm going to begin by selecting a fluid structure interaction template. The template includes a number of options. I'll select the appropriate options for my simulation and go ahead and execute the template. The template is now completed. I prepared this geometry using SpaceClaim. It consists of an 8-inch pipe, valve, and elbow assembly. For my simulation, I'd like to compute the deflection of the reed sensor based on the position angle of the valve. The template has also defined a simulation workflow. I have a series of tasks defining the fluid structure interaction simulation. By following the task workflow, AIM will guide me through the entire simulation process. I'll begin by only selecting the parts that are required for my simulation by using the configuration tasks. I'll suppress the solid geometry, leaving only the flow volume for the fluid simulation. I'll also suppress the geometry not required for the structural simulation, leaving only the reed sensor. Next, I'll select the mesh task for the flow simulation. I can use the Fix option to quickly navigate to any model input that requires my attention. Here I need to define the surfaces for inflation. Specifying inflation will create layers of prism elements adjacent to the fluid wall boundaries. Once inflation is specified, I'll simply accept the default mesh settings and update the mesh task to generate the mesh. Once the mesh is complete, I can review the mesh density before continuing with the problem setup. You will see that I have 3 inflation layers on the fluid walls, and that AIM has automatically refined the mesh to accurately resolve all of the geometric detail. Next, I'll move to the physics task to continue with the model setup. First, I'll define a material assignment of water for the fluid region by selecting water from the AIM material library. Next, I'll apply the boundary conditions. First, I'll select the inlet, and I'll apply an inlet pressure of 5,000 pascals. Next, I'll select the outlet, and I'll apply a static gauge pressure of 0 pascals. And finally, I'll specify a fluid wall boundary condition by allowing AIM to automatically select all unspecified surfaces for the fluid wall boundary. Now I'll execute the solution. I'll update the results task, and this will execute the solution and compute the fluid results. Once the solution is complete, I can review the final residual values and post-process the results. I'll review the fluid streamlines, which show how the fluid flows through the pipe and around the valve. I can also review quantitative results, such as the mass flow rate at the outlet, which is about 55 kilograms per second. At this point, I'll proceed with the structural simulation. I'll accept the defaults for the structural mesh and move straight to the physics task to set up the structural simulation. First, I'll change the material assignment for the reed sensor to polyethylene. Next, I'll specify a fixed support to constrain the base of the reed sensor. And I'll use the Fix option to quickly navigate to the physics coupling interface. Here I'll specify all the surfaces of the reed sensor to receive the fluid force, which includes all the surfaces except for the fixed base. Now I'll go ahead and execute the solution. I'll update the results task, and this will generate the structural mesh, execute the solution, and compute the structural results. Once the solution is complete, I can post-process the results. I can review the deformations of the reed sensor. I can also review the equivalent stress results, and also animate the equivalent stress results. Now that the fluid structure interaction solution is complete, I'd like to move from a single value analysis to a design point study. I'll identify the valve angle as a parameter, and in a similar manner, I'll go ahead and define the mass flow at the outlet as a parameter, And I'll also define the maximum deflection of the reed sensor as a parameter as well. Now from a single value setup, I have a parametric study defined. I'll define additional design points to evaluate the maximum deflection of the reed sensor and the mass flow at the outlet over a range of valve angles. And now with a single mouse click, I can execute the entire solution for all of the design points that I've defined. The design point solution is now complete. I've solved for both the maximum displacement of the reed sensor and the mass flow at the outlet over a range of valve angles. I can also return to the study and review the results for any of the retained design points. I can simply select the design point that I'd like to review, and then review the fluid results, such as the fluid streamline shown here, and I can also review the structural results, such as the deformations. To recap, in this demonstration, I've used ANSYS AIM to perform a fluid structure interaction simulation to evaluate the impact of the valve angle position on the mass flow and the reed sensor deflection. Thank you for watching this demonstration of ANSYS AIM.